Welcome back to ECE 220. We are in the week of exam number 1. Exam number 1 is Thursday, and if you normally make plans to leave at 10:20, I'm going to go ahead and give you a full hour to take the exam, not just 50 minutes. You will have until 10:30, and then I will immediately collect those, and then you're free to go. You're free to go if you finish it at 9:32, but hopefully you're not quite that quick. But if you are, great, then you really know your stuff. But we'll have the exam from 9:30 to 10:30 on Thursday. Lab number 1 starts this week for Group A. And so depending on your section, you will go to lab on Tuesday, Wednesday, Thursday, or Friday. Homework number 4 is due tomorrow on Tuesday. If you want to solve any of these problems, or if they're begging for a solution via simultaneous equations, Appendix A is hopefully helpful. And if you have questions on that, let me know and we can try to work through that. We are alternating weeks, which means Group B, which I think is Section I. Your pre-lab is due this coming Saturday. Hopefully everyone in Group A submitted their pre-lab on Saturday. Looked like a fair number did. And if you're keeping up with the readings, this week we will finish Chapter 4. We are going to be finishing or working through sections 9 and 13 in Chapter 4. That means that we're trying to learn more strategies for helping us solve circuit problems. And today's strategy is source transformations. Can we transform a voltage source in series with a resistor into a current source in parallel with a resistor, or vice versa? Those are the transformations that we will utilize to help us analyze circuits, or maybe more effectively solve a given circuit problem. If these two sources are to be equivalent, then we need to figure out what makes them equivalent, and typically we compare the terminals of those sources, terminals A and B. If their open circuit voltage and their short circuit current are the same, then those sources are equivalent. That's how we will demonstrate that these two circuits are equivalent at the terminals, at A and B. You go into the source, all bets are off. The power, this is the caution, these two sources have different power properties, or they consume power differently. And we'll show that in this part of the class with the caution. Then we'll look into how we can analyze a circuit using these source transformations by going forward and backward through the circuit. And you might hear this described as ladder analysis. So we'll put a ladder on its side, and the circuit sort of looks like these rungs and the side of a ladder. The resistors are making up those a side and the rungs of a ladder, and we're working our way up and down that ladder, although it's on the ground horizontally, so maybe it's a little safer. But we'll do circuit analysis by source transformations. And again, the caution sign or symbol is, if you want to be determining power in a circuit, you probably don't want to be messing with source transformations. If somebody says, what are the power characteristics of this, unless you go back to the original circuit and analyze the power characteristics. Here are the two sources that we will be able to essentially interchange. We have the two terminals A and B, and we want to determine how are these circuits related to make them equivalent. How are these sources related to make them equivalent? And we will derive what this current source needs to have in terms of a value to make these two sources equivalent. Tomorrow we'll talk about essentially simplifying a messy circuit into one of these sources, and we'll call that the Thevenin equivalent if it's a voltage source in series with a resistor, or if we make that source look like a current source in parallel with a resistor, we'll call that a Norton equivalent. Sometimes that's easier if we're hanging different loads across terminals A and B. It might be nice, instead of reproducing all of the circuit analysis, can we now make an equivalent, make a Thevenin equivalent of everything to the left of terminals A and B, if that was just a mess of circuit, a messy circuit to the left of terminals A and B. Can we now make it look like a Thevenin equivalent or a Norton equivalent? And we'll learn strategies for finding those equivalent circuit models for a mess to the left of terminals A and B. Probably that will be tomorrow. But today we want to get comfortable switching back and forth or replacing voltage sources in series with a resistor with their equivalent current source in parallel with a resistor. And it's no coincidence that resistor is the same. That R is the same in both. We now just need to figure out how do we describe I in terms of V and R. So we want those to have the same behavior at the terminals A and B. And if those are going to have the same behavior, then if we put a voltmeter across those terminals and measure the open circuit voltage, we better get the same measurement in those two circuits, in those two sources. The Thevenin and the Norton better give us the same open circuit voltage. If we put an ammeter across and just presented those two terminals with a wire, what's their short circuit current between terminals A and B? That better be the same for those two sources. We're then talking about open circuit voltage and short circuit current. Let's now derive those for the two different sources. Here's our Thevenin source with a voltage source in series with a resistor. And if I'm now trying to find the open circuit voltage, I'm trying to find that voltage. And if I need to find that voltage, maybe I need that I. In this source, what is I? How much current is flowing through that resistor R? Is it V over R? Is that the current flowing? Pardon? So now it's the voltage of across that resistor divided by R. What's the voltage? So now we're kind of going in circles, maybe. This is open circuit. What's the resistance seen at VOC? It's an open circuit. How much current flows in an open circuit? 0. So I, in fact, in this configuration of a source is 0. If we now see that and we now say, well, let me do a KVL, we now know that minus V plus RI plus VOC is equal to 0. But we just realized that in an open circuit there's no current flowing through those terminals or across terminals A and B. So this now says that minus V plus VAB is equal to 0. Whoops. I'm calling it open circuit. V open circuit is equal to 0, or V open circuit is V. The open circuit voltage, if you put a voltmeter across terminal A and B, you better measure V. That's the open circuit voltage. What's the open circuit voltage here? We can label it similarly. Now what is, maybe I should call this something else. Can I call this, I don't know, let me call it I sub 2 to distinguish it from I1. So here's I1 and there's I1. What's I2? This you definitely need to know for the exam on Thursday. Even though we're talking chapter 4, this is beginning chapter, I don't even know. This is Ohm's law, isn't it? What's I2? Oh, I'm sorry, I'm getting ahead of myself. Ohm's law we will use to get V open circuit. But how much current is flowing through that resistor? It's just I. I's not going out to terminal A, is it? Because that's an open circuit. If you did KCL right here, can you convince yourself that all of capital I is going to little I sub 2? Little I sub 2 is now I. Now I'm ready to do open circuit. This is Ohm's law. That's Ri. In this case, it's Ri sub 2, and that's R times I. Now, if these two sources are equivalent, we need their open circuit voltages to be the same. That means that V needs to be equal to Ri. And now do we have a relationship for I, our current source in the Norton equivalent? Now we can solve this for I. And if we want these two sources to be equivalent, then we make I equal to V over R. If somebody gives us the voltage in that first source, which we're calling the Thevenin source, then if somebody says, well, transform that into its Norton equivalent source, then you would make a current source have a value, V over R, and put it in parallel with that resistor R. And then they would share the same open circuit voltage. Now, is that going to be the same when we start looking at the short circuit current? Let's now look at I short circuit 1. What is that? I've put a wire between A and B, and I now want to measure what's the current flowing through that resistor R. That's the same current that's flowing between terminals A and B on that wire. It's the same current going through that voltage source. This is Ohm's law. Which is V over R. All right, well now let's go down to this source and short it. What's I short circuit sub 2? How does current like to flow? Least resistive path. Is there any resistance in that short circuit? No. So all of your current is going to go through that wire. All of I is going to go through that short between terminals A and B. Or if you go, I'm not feeling it. Well, do you feel a current divider? Could we do a current divider? How would we do a current divider? If we now applied the current divider formula, what would that be? We're dividing that I between R and the wire. And we want the current in the wire. How do we get the fraction of I that goes through that wire using our current divider formula? This has to be second nature by Thursday. Yes? It's R over R plus 0. Because we take the opposite, or let's say the opposite resistor, and divide by the sum of the two resistors. Now I have R over R, 100% of I goes through that wire. That maybe makes you feel like the first answer was correct. So this is now I. Again, if these two sources are equivalent, what do we need? We need the short circuit current to be the same in both. And isn't that what we derived when we compared the open circuit voltages? I needed to be equal to V over R for those two sources to be equivalent. If you want to replace that voltage source in series with a resistor with a current source in parallel with a resistor, you keep the same resistor, but you make the current source have a value of V over R. And then you can replace the source at those terminals A and B. Let's see if this makes sense when we apply a resistor to terminals A and B. Let's check the equivalence. What's I in this circuit? This is now our Thevenin equivalent. That's what this is. This is our series source, our voltage source in series with a resistor. What's I? And you have to have this just quickly on exam on Thursday. What's I? V over the total resistance across that, right? That's I. This is now V over R plus R sub L. That's I. What about for this source? What is I? Oh, and let's just go ahead and say, well, let's call this I for now, but in our back of our head, we're saying that's supposed to be V over R. If we're now using this as an equivalent source. What is little I? What's the formula for little I? That's a current divider, isn't it? It's the other resistor over the sum of the two times the current going in, which is I. But if we now replace this with V over R, This is better than pulling a muscle, but I'm celebrating. Do you see that those two are the same? It's consistent. We've verified or validated this opportunity to change or replace one source structure with another. Now that I've got us all excited, let's put some brakes on. Let's slow down a little bit. If somebody now wants to start talking about the power to the left of terminals A and B, say, wait a minute, we didn't say that. We just said that at the terminals A and B, what's to the left will supply the same behavior at terminals A and B, whether it's a Thevenin or a Norton source. We said nothing about the power to the left of those terminals. And let's now show that we can't be thinking about power in the two sources. What's the power in the Thevenin source? Again, this is kind of a review for Thursday. If I said now what's the power dissipated, let's say the power dissipated in that source, the power dissipated is really in that resistor R, is it not? What's the power of that resistor? What's the power associated with that resistor? If I draw that. Isn't it Ri squared? And what's the I? What's the current? 0. That source dissipates 0 watts. What about this guy? And let's go ahead and just say this is V over R. What's the power dissipated in R? Can I do that? Can I say, well, if I knew the current through R, it would just be Ri squared. What is I? It's the source's value, which is V over R. We'll square that, and we end up with something that's definitely not the same as what we had in the Thevenin source. We had no power dissipated in the Thevenin source. Now we have V squared over R in the Norton. These are not giving rise to the same kind of power behavior. So don't do power after you've replaced one source with another to the left of terminals A and B. You still can worry about power to the right of A and B, which is the whole point of doing these equivalents. Let me just summarize. I'm just going to quickly read to you a bedtime story. No, shouldn't have said that. Then you'll start sleeping. So whatever gets you awake. Our morning reading, how's that? Coffee. This is our coffee. So now the terminal characteristics at A and B of these sources are identical. That's our summary. That means that any voltage source, V sub S, in series with a resistor R can be replaced with an equivalent current source, independent source, V sub S over R in parallel with a resistor R. The resistors are the same in those two sources. One's in series, one's in parallel. One's a voltage source of value V sub S. If you know that, then you know the current source's magnitude. That's V sub S over R in the Norton equivalent. This is what you can do. You can swap one with the other if you're just worried about what's happening at terminals A and B. Maybe the right-hand side is easier for the analysis of the problem that you're studying. I'm saying with the parallel resistor, the current source magnitude is V sub S over R. If you know V sub S, if you knew I, then the Thevenin would be IR, voltage. They're related by Ohm's law, which if somebody now provided you with a dependent source and said, well, I really don't like it as a dependent voltage source, oh, well, let's make it a dependent current source in a new structure and then worry about what happens to the right of terminals A and B. All right, you're going, I have no idea where he's going with this. Let's do a problem. Let's put this into reality. Suppose now that somebody gives you this circuit and they say find I sub 0. And now you're going to go, can we do this on exam 1? I'm going to say it's multiple choice, so if you do this, if you do it right, you're fine. You do it wrong, yeah, you'll get it wrong. But how would you have done this using chapters 1 through 3 analysis strategies? You'd probably collapse all of those resistors down to an equivalent, find the current coming out of that source, and then work your way back to the right. Oh. In this strategy, what we're going to do is we're going to work our way from the left to the right and leave I0 alone, so that at the end we can immediately find I sub 0. We want to now apply source transformations and make this circuit as it looks now. We now want to simplify that into something that maybe looks like this. And we'll call these Thevenin resistance and Thevenin voltage if we have it in the series combination. Boy, that's an ugly circuit, isn't it? Let's clean it up just a little. But on an exam, you're not going to lose points for neatness. Did I say that? It's multiple choice. So the neatness comes in bubbling. You need to make sure that your bubble is cleanly bubbled dark if that's your answer. We want to do this. Now you could quickly solve this problem for I sub 0. Yes? I0 is just V Thevenin over R Thevenin plus 80. What we want to do then is change all of this mess to the left of AB into something that will eventually look like that. That's our goal. This is our goal. So let's start. Do you see that if I converted that voltage source in series with that resistor into a Norton equivalent source, I would then have a current source and a 36 ohm resistor in parallel with another 36 ohm resistor. Let me draw what I'm trying to say. I now want to make this my first step, and maybe what I should do is call this A1 and this is B1. So here is A1 and here is B1. I'm going to now, to the left of A1 and B1, replace that with its Norton equivalent, so that everything to the right stays the same for now. How much do I have here? Now, the only thing that I need to, because I said that this resistor stays the same when going from a Thevenin source to a Norton source. What is this? What's the value of my current source in my Norton equivalent? V over R. What was V? 360 divided by what R? 36. 360 divided by 36 is isn't that 10? So now this source is 10 amps. Are we okay with what I've done so far? I've simply replaced that Thevenin source with its Norton equivalent. But now, here comes the fun part. You know how to combine those two resistors in parallel. What is 36 in parallel with 36? Isn't that, in formula terms, but we have a lot of 36s there, don't we? Isn't that just 1/2 of 36, or 18? Which means that now I can combine that, and if I now call this A2 and B2, I now can say that, oh, I have 18, 2, 10, and then everything else. This was 20, is that right? And 80. Can I now say this is terminal A2 and B2? Now do you see what I want to do? I want to convert that back into a Thevenin source. To the left of A2, B2. What will the resistor be? So everything to the right of A2, B2 stays the same. How do I place a value on that resistor? If I'm now converting from a Norton source to a Thevenin source, how does the resistor change? Does it change? No, it stays the same. So that's 18. What's my open source voltage across terminals A2, B2, or what's the voltage source value here? If you virtually erased everything to the right of A2, B2, what would be that voltage dropped across A2, B2? I'm covering it up if you can't tell. I've now covered up the circuit to the right of A2B2. What's the voltage dropped across A2B2? 18 times 10, 180. That's this V. This V is now 180 volts. What can we do now? Do you see where I'm going with this? 18 plus 2 is 20. I can combine those. Now I can convert that Thevenin into its Norton equivalent. Meaning I now have A3, B3 and what's going to be to the left of A3B3? If I want the Norton equivalent of a Thevenin that has a 180 volt source and a 20 ohm resistor, what's this resistor value going to be? Isn't it the 20? And what's my current source? I had a voltage source of 180 and a resistor of 20. Isn't that what that is? Which is 9. Now what can I do? Hint, hint. I have 20 in parallel with 20. That becomes 10. And I now want to flip it into a Thevenin. Or let me just do one more step. Now what I've done is I now have this 9 with 10. And if you wanted to find I0 now, you could, couldn't you, with a current divider. But let me go one more step because I promised my goal, I didn't promise, I said my goal was to get a Thornton, a Thevenin source. This is a Norton source, but let me go one more step and convert this into its Thevenin equivalent to the left of AB. What would the resistor be? What's the resistor? Isn't it the same as the resistor in the Norton? This now becomes 10. What's my voltage source in the Thevenin? What would be my open circuit voltage across terminals AB if I removed that 80 ohm load? 9 times 10, wouldn't it be 90? Now do you see what I0 is? Maybe you knew that all along. Did you know that initially from the circuit that you were given? Probably not. But now we have I naught, the current flowing in that 80 ohm resistor. Now we know that's 1 amp. What if somebody said, well, I actually am interested in the power of everything in this original circuit? Well, that kind of, if you did mesh analysis, how many mesh currents would you have here? 3. If you did node analysis, what would you have? 3 essential nodes, so you'd have 2 unknown node voltages. So you'd have a 2 by 2 or a 3 by 3 to solve. Now maybe you don't like what we did, but this was kind of easy, wasn't it? Each step was just a fairly straightforward step, and now we ended up with an answer. Let's build that ladder back to what it was to begin with. Suppose now somebody said, well, what about the power associated with the original circuit? Well, let's just say circuit elements. And if you really wanted to be difficult, you could say, I want to know what the power is of that 360 volt source. Well, now let's go back and start building from what we know. We know at terminals A and B, we found I sub 0 is equal to 1 amp, and we knew that this was 80 ohms. Can you tell me anything about this voltage? Let me call it V sub 0. Isn't that Ohm's law? That's R times I, where R is 80 and I is I sub 0, 1. So that's 80 volts. We know now the voltage dropped across terminals A, B in our circuit is 80 volts. Well, that means let's go back to what we have. Here's A and here is B. And in our circuit, if we kind of work our way back, wasn't this 20 ohms? And now, well, let me put it here. Can you now tell me what I1 is flowing through that 20 ohm resistor? Isn't that Ohm's law? What's I1? Isn't that V naught over 20? Do you see what I'm doing? I'm working now back towards the source. If I know I1 going down is 4 and I sub 0 going down is, I sub 1 is 4, I sub 0 is 1, what's I sub 2? we can apply KCL to that node. KCL at that node, let me call that node A, capital A. KCL at A says that I sub 2, the current in, is equal to the current out. I sub 2 flowing in that branch is 5 amps. Well, now we can go back even further in our circuit. What was this one? This one was 2. And now we found I sub 2. All of these we've already found. Can we now find that? Did I call that? I haven't used V sub 2 yet, have I? What's V sub 2? Can we find V sub 2 with the given information? Isn't V sub 2 Ohm's law? Now, can you see that if somebody asks, what is this voltage across that resistor, which that resistor was, we're all the way back to 36 ohms. Can you now find V sub 3 in that circuit? You know V sub 0, you know V sub 2. We just can do a KVL and find what V sub 3 is. KVL, this we're kind of reviewing for the exam, if you hadn't noticed. KVL now, right here, is minus V sub 3 plus V sub 2 plus V sub 0 is equal to 0. Or V sub 3 is V sub 2 plus V sub 0, which was 10 plus 80, which is 90 volts. If that's the case, can you now tell me what this is, I sub 3? If we know the voltage dropped across a resistor, can you tell me what the current is? That's Ohm's law. I sub 3 is now V sub 3 over 36. This is just Ohm's law. That ends up being 2.5 amps. But it worked so well at A, can we do the same thing at B? What do I want to call this? I sub 4? What's I sub 4? Can I apply KCL at B? I sub 4 in equals I sub 3 out plus I sub 2 out. And I know those. KCL at B says I sub 4 is equal to I sub 3 plus I sub 2. And what was I sub 2? 5. And this was actually 36 ohms. We're back where we started, aren't we? How much current is flowing through our 360 volt source? Isn't that I sub 4? What's the power of our 360 volt source. This is now, if we used our passive sign convention, that would be a negative, and this is now I sub 4 minus 360 times 7.5. That ends up being minus 2,700 watts absorbed, or that 360 volt source is delivering or supplying or supplied to our circuit 2,700 watts. Thank you for your patience. I'm way over time. We'll pick up somewhere close to those sources next time.